Welcome to Lecture 3.6, Real versus Complex Fourier Series. Last time, we derived formulas for the complex Fourier series of a function. Let's recall what those were. If f of x is a piecewise continuous 2L periodic function, then we can write it as a potentially infinite sum of complex exponentials. Now, last time we did the case where it was 2 pi, not just 2L, but it should be easy to see how and why this generalizes. So we can write f of x as the sum from n equals negative infinity to positive infinity of Cn times e to the I pi n x over L. Now the reason why this works, the key here, is that these complex exponentials form an orthonormal basis for the space of 2 pi periodic functions. So I write that as follows over the complex numbers. And again, we're slightly abusing notation by allowing infinite sums, but we can get away with that. So we showed last time why it was orthonormal. I didn't actually prove it was a basis. That's a very technical, advanced result that we can write everything using these, and they are linearly independent. That's not clear. We just showed they were orthonormal. But if you don't like this doubly infinite sum, so n going from negative infinity to positive infinity, we can just pull out the zero term, C naught, and then we can write a regular infinite sum from n equals 1 to infinity of these two things. So we can group the positive n and the negative n terms together like this. So we derived formulas for the coefficients. Because this is an orthonormal basis, each of the coefficients is just what we get when we project f onto that corresponding basis function. So C naught is just the inner product of f with 1, the projection of f onto 1, which is 1 over 2L times the integral from negative L to L of f of x dx. And Cn, it works for positive and negative n, you don't need to compute it twice, is just the inner product of f with e to the I pi nx over L, and that's the same integral, except we have an exponential function here. So 1 over 2L times the integral from negative L to L of f of x e to the negative I pi nx over L dx. In this lecture, we will see how to go between the real and the complex version of a Fourier series. So that is, if we are given the complex coefficients, we'll see how to derive the real coefficients, the ANs and the BNs, and vice versa. Sometimes it's really easy to derive one of them directly using the integral definitions, but not the other, or vice versa. And this is just a simple application of the following identities that we've already seen. So Euler's formula, remember, is e to the I theta equals cosine of theta plus I sine of theta. And if you plug in negative theta into here, and you get e to the negative I theta is cosine of theta minus I sine theta. Remember, negative signs absorb in the cosines and pull out of the sines. And then if we add these two formulas and divide by 2, we get a formula for cosine of theta, which is e to the I theta plus e to the minus I theta over 2. And if we subtract these two and divide by 2i, then we get sine of theta equals e to the I theta minus e to the minus I theta over 2i. Now, in the previous lecture, I spent about 5 minutes or so going over these and drawing pictures with the unit circle. So if you didn't watch that lecture, please go back and watch that one first. Here's the first result out of 2. This is how to go from the real to the complex Fourier series. So let's suppose that we have a function f of x and we know its real Fourier series. So we know the ANs and the BNs. And here's how we get the complex Fourier coefficients from that. So Cn is AN minus IBN over 2, and C minus N is AN plus IBN over 2. So let me show you why this is true. So f of x, so let me write the Fourier series down here is a naught over 2 plus n equals 1 to infinity of an, I'm going to do this, I'm going to write this an cosine of n pi x over L, so I'm going to write cosine in blue and then plus bn sine of n pi x over L. I'm going to write that in red. So now we are going to use those formulas for cosine and sine in terms of complex exponentials. So this is a naught over 2 plus n equals 1 to infinity of an. And now we have e to the n pi x I n pi x over L plus e to the minus I n pi x over L all over 2. Remember, that's our formula from the previous slide, but now here theta is equal to n pi x over L. And then we get plus bn, and then this becomes e to the I n pi x over L minus e to the minus I n pi x over L all over 2I. So now we need to collect terms. So let's put these exponentials with positive n's together and put the ones with negative n's together. So if we do that, we get a naught over 2 plus n equals 1 to infinity. Okay, so how many, let's see, how many e to the I n pi x over L's do we have? And how many e to the negative I n pi x over L's do we have? So what goes here? So we have an an, and then we have a an over 2, and then here we have a bn over 2I. Now, I don't like to have i's in the bottom, so let me move the I to the top of this and make that negative. So I'm gonna do this. I'm gonna make this a negative, and I'm gonna put this I, move that I up top. Okay with that? So now, how many e to the I n pi x over L's do we have? Well, we have an over 2 minus bni over 2. And that's exactly what we have right here. So that's where that comes from. So this is an minus I bn over 2, which is literally collecting terms. And now, how many of these e to the negative I n pi x over L's do we have? Well, we have an over 2 of these right here, and we have minus times negative, so positive bni over 2 of these. So this is an plus I bn over 2 times this. So remember, a complex Fourier series. Now I'm going to pick a, let's see, I'm going to pick a different color. Which one should I pick? I'll pick this orange. The complex Fourier series is C naught plus n equals 1 to infinity of Cn e to the I n pi x over L plus C minus n e to the negative I n pi x over L. So what this means is that C naught has to be equal to a naught over 2. The constant terms have to be equal. So let's put equal sign there. Cn is, by definition, the coefficient of this exponential. So Cn equals an minus ibn over 2. That's what we got right there. And then C negative n has to be an plus ibn over 2. And that's this thing right here. So we just verified these two things. I didn't actually tell you about this one, but I claim that just partially coincidence, partially mathematical, that if you, well, let me add this here. Let's say C naught equals a naught over 2, but in fact, that's actually a special case of this formula right here, Cn. If you declare, if you say when n equals 0, look what happens. You get C naught is a naught, and then there is no such thing as b naught, so let's just make that 0. So if you plug in n equals 0, you get C naught is a naught minus 0 over 2, and you get this formula as well. So you don't need to remember this extra formula. Just know that this works for all n positive or minus or negative. And this is why. It's literally just take the real Fourier series and plug in these formulas for cosine and sine and collect terms, and that's all there is to it. Okay, so here's the opposite of the previous slide. This is how to go from the complex to the real Fourier series. So let's suppose that we have a function f of x, which is written as a complex Fourier series, like this. And as we know the cn's, then we can derive the an's and the bn's from these. So we can say that an is cn plus c negative n, and bn is I times cn minus c negative n. Okay, so really all we're going to do here is just apply Euler's formula. This is e to the, remember, I theta equals cosine of theta plus I sine of theta. But we can't do it from here directly. Well, I guess we could, but then we would get this doubly infinite sum from negative infinity to infinity. Well, that's not wrong. It's not the form that we want it in. We want it as a sum from 1 to infinity. So what we're going to do is we're going to write f of x as c naught, pull out the constant, and then n equals 1 to infinity of cn e to the I think I'm going to write I n pi x over L. So it doesn't really matter whether we put the n or the pi first. And then plus c minus n e to the minus I n pi x over L. And then we will apply Euler's formula to both of these. And recall that e to the negative I theta is cosine of theta minus I sine of theta. Okay, so this is essentially what we're going to do, and then we're just going to collect terms as before. Okay, so let's see what we want to do. I'm thinking if I want to use different colors again. Plus n equals 1 to infinity. Cn. So yeah, I'll use blue for this first one. I'll say this is cosine of n pi x over L plus I times sine of n pi x over L. And then plus c minus n times, so we subbed in for that, and now let's sub in for this one. So this is cosine of n pi x over L minus I sine of n pi x over L. Okay, so now as before, let's collect terms. Let's put the cosines together and put the sines together. So c naught stays the same. Now we have the sum from 1 to infinity. And how many cosines do we have of n pi x over L? So we have some number of cosines, and then we have some number of sines, sine of n pi x over L. Okay, so let's see. I'm going to use different colors again. So what goes? So what goes here? How many cosines? So we have a cn times a cosine, and we have a c negative n times a cosine. So we have cn plus c negative n. And notice that's exactly what that is right here. So now what goes here? Here we have how many sines do we have? We have cn times I, and here we have c negative n times negative I. So this is just I times cn minus c negative n. And that's exactly what we have up here. So that's why these things hold, and let me just write that as, so if we were to write the complex Fourier series, sorry, the real Fourier series, this is a naught over 2 plus n equals 1 to infinity of an cosine of n pi x over L plus bn sine of n pi x over L. And now we have, oops, I think I switched my color scheme from the previous slide, but that's fine. What have I not used in a while? I'll go back to red. And so these things are equal. So these coefficients have to be equal, and these have to be equal as well. And once again, we don't have to do any special cases when n equals 0. It just happens to work out perfectly. Notice that if n equals 0, then we get a naught equals c naught plus c0 plus c negative 0. And look what that is. That says that c naught equals a naught over 2, and that's exactly what we got down here. So this formula holds for n equals 0 as well. And there is no b0, but if you were to try to plug in n equals 0 into here, you would get that b0 is c0 minus c0, which is 0. Okay, so as before, nothing special. It's just an application of Euler's formula and then collecting terms. We'll conclude with two examples. The first one, we'll start with the real Fourier series and impute the complex Fourier series, and then we'll do it in reverse after that. So we'll start with computing the complex Fourier series of our favorite square wave. Let me sketch this. So here it is. Now we've computed both the real and the complex Fourier series of this guy before. So we know how to do this, but I'm just going to show you how to compute the complex Fourier series from the real series. So this is pi, this is 2 pi, this is negative pi, and this of course is 1 and negative 1. Okay, so I think when we computed the complex Fourier series of this exact function in the previous lecture, but when we computed the real Fourier series, this was way back when we learned about Fourier series in lecture 3.2, something like that. We did it where the function had period 2 instead of period 2 pi. But that doesn't actually change anything. It doesn't change the coefficients. What it does change is instead of writing bn sine of n pi x, so this is what we write when L equals 1. Instead we write bn sine of nx when L equals pi. So the only difference here are these is this pi in here. The actual coefficients don't change. Now that's maybe not completely obvious, but I encourage you to think about it and convince yourself as to why that is. And you should see it pretty easily without much trouble. Okay, so let's compute the real Fourier series. I know we've done it before, but just to iterate or just to emphasize how simple it really is. So this is an odd function, so a naught and an are 0, and bn, since it's odd, we go from integrate it from 0 to pi. Let's take 2 over pi times the integral of f of x, which is 1 times sine of nx. Okay, so what is that? That is 2 over n pi times 1 minus negative 1 to the n. So those are the real coefficients. That was much easier than computing the complex coefficients that we did before. So let's compute the complex coefficients. So c naught is the average value. That's equal to 0. So c naught is 0. And cn, we just use our formula. We use an minus I bn over 2. So the an's are 0, so this is negative I bn over 2, which is, so we take this and we divide by 2, so we get rid of the 2 and we stick a negative I up front. So we get negative I over n pi times 1 minus negative 1 to the n. Now there's several ways to write this. If we put the I in the bottom, then the negative sign goes away. Or if we want to make this negative sign positive, then we could switch the order of these two. But this is Cn. And I claim we're done. You may be wondering, what about C negative n? Well, we don't actually have to compute that. We didn't compute that in the previous lecture when we computed the complex Fourier coefficients. Cn is what you get by just taking this formula and plugging in negative n. Sorry, C negative n is what you get by taking this formula and plugging in negative n. What happens? The negative n here doesn't change anything. And if you plug in negative n for n here, then this becomes positive. So let me just convince you of that if you don't believe me. C negative n is an plus I bn over 2. So that's positive I bn over 2. And that's I over n pi 1 minus negative 1 to the n. And remember that negative 1 to the n is negative 1 to the negative n if n is an integer. And notice that this is what you get by taking this and plugging in negative n in place of n. And this was always the case. For the complex Fourier coefficients, we didn't have to compute Cn and C negative n separately. And we don't need to do it here either. So to summarize, this square wave, f of x equals n equals negative infinity to infinity of I over n pi times 1 minus negative 1 to the n times e to the I n x, and we should really say n is non-zero down here because we're excluding the n equals 0 case because the constant term is 0. To summarize what we've done, if you remember the previous lecture, we computed the complex Fourier coefficients of this directly. Remember, we said Cn was 1 over 2 pi from negative 1 to 1 f of x e to the I n x dx. And for this, we had to break it up into two pieces. We needed to do 1 over 2 pi times negative 1 to 0 of e to the negative I n x dx. And then we had to, negative 1, because the function is negative 1 down here, plus 1 over 2 pi times 0 to 1 times 1 times e to the negative I n x dx. So we had to do these two things separately, and it was more complicated. I think you'll agree that it was easier just computing this bn and then literally plugging it into this formula and getting out this thing right here. So this is one case where it's easier to compute the real coefficients and then use the formula to find the complex coefficients. In the next example, we're going to do one where it's the opposite. Here's that example. Compute the real Fourier series of the 2 pi periodic extension of the function e to the x defined from negative pi to pi. So let me sketch this first. This is an example that we actually did in the previous lecture. So let's say that this is negative pi to pi, and this is 3 pi and negative 3 pi. And this function e to the x, negative pi to pi, looks like that. And then if we make it periodic, extend it, it's going to look like this. So this is f of x. Now, if we were to compute the real Fourier series of this, which is what we want, then a naught is going to be 1 over pi from negative pi to pi of e to the x dx. That's not too bad, but a n is 1 over pi from negative pi to pi e to the x cosine of nx dx, and bn is 1 over pi times negative pi to pi times the integral from negative pi to pi of, oops, not s. We need an e to the x first, e to the x times sine of nx dx. And these things are both nasty integrals. Remember how to integrate e to the x cosine? You got to integrate by parts twice. And then when you do that, you have to set what you got equal to the original thing. And then it's nasty. I mean, you could use a computer too, but you still have to do it 3 times. So here I want to show you, so the previous slide I gave you a Fourier series where it was computing the real Fourier series was easy. So if you wanted the complex one, it's easier to compute the real one and use our formulas. Now we have one where computing the real Fourier series is hard and complicated by the nature of the function. So if we want the real Fourier series, it's easier to compute the complex Fourier series. and then just use our formulas. Okay, so instead we will compute C naught. Well, we did this in the previous lecture. So if you haven't watched that, please watch that now. But I'll at least write out the formulas so you see how they're not that hard. C naught is 1 over 2 pi times the integral from negative pi to pi, e to the x dx. Notice that that's off by a factor of 2 of a naught, as we've already seen. And then Cn is 1 over 2 pi times the integral from negative pi to pi. Now let me tell you what C naught was. That ended up being 1 over 2 pi times e to the pi minus e to the minus pi. And Cn was the integral from the integral of e to the x times e to the negative inx dx. That's not too hard to compute because all we have to do is combine these exponents. So e to the 1 minus in x dx. And if we did that, and we plug in the limits, we end up getting is negative 1 to the n over 2 pi times 1 minus in times e to the pi minus e to the minus pi. Okay, so now we want to use our formulas for an and bn. And let's write down what those things are. Remember that they're actually really easy. An is Cn plus C minus n, and Bn is I times Cn minus C minus, instead of C, I wrote an E, Cn minus C minus n. Now even though we have a Cn here, we don't need to compute C negative n separately. All we need to do for C negative n is just plug in negative n into this. Okay, so what can we say? So first of all, I mentioned this at the end of last lecture. Some of you may not like the fact that I have an I in the bottom of this here, because we can't easily break this apart into the real and imaginary part. So just for cleanliness' sake, I'm going to get rid of that. So let me say that note is that 1 over 1 minus I times n. That's what we have here. I'm going to multiply by the complex conjugate, or multiply by 1 plus in divided by 1 plus in. So now if we have this, the bottom of this fraction is difference of squares, 1 squared minus in squared, so that's 1 plus n squared, and the top is 1 plus in. So now we can see, if we want to, this is the real part is 1 over 1 plus n squared plus I times n over 1 plus n squared. Just a little nicer way to do it. So now, using that, I'm going to write, I still prefer this because it's more compact. So what I can do is I can stick this in for here, and I can write this Cn. So instead of dividing by 1 minus in, I can divide by 1 plus n squared and multiply by 1 plus in on the top. So I'm going to write this Cn as, let's see, so negative 1 to the n times e to the pi minus e to the minus pi. At the bottom it's 2 pi times 1 plus n squared. That's all real. And now I'm going to multiply this by 1 plus in. Okay, so this is Cn. Okay, so what is C negative n? So C negative n is what we get if we just plug negative n into here. And now it's easy to see that, well, this n doesn't change because negative 1, remember, negative 1 to the n equals negative 1 to the negative n if n is an integer. So this n doesn't change, this n squared doesn't change. The only thing is, instead of this plus in, we get minus in. So c minus n is just the complex conjugate of that. I'll let you think if that always happens or when that happens. It's a good little exercise, or what it means when it happens. Anyways, so c minus n is negative 1 to the n times e to the pi minus e to the negative pi. And I'll give you a hint for that. If you think about the complex Fourier series, we have Cn times e to the in x, and then we have c minus n equals I to the negative in x, and notice that this is equal to e to the in x, just the complex conjugate of that. Okay, so back to here, this now. So let's divide by 2 pi times 1 plus n squared. And now we have 1 minus in. So this is equal to Cn complex conjugate. Okay, so now what do we get when we, well, let's see, an, let's write that down. So an is just these two things added up. So what happens? Well, the imaginary parts cancel because we have a plus and a minus. And then these things double up, so we can get rid of that too. So an is Cn plus C minus n, which is this thing that I've boxed, but without the complex part and without that 2. So that's negative 1 to the n times e to the pi minus e to the minus pi over, there's no 2, so over pi times 1 plus n squared. So that's e to the n, that's an, and then I should probably do a naught as well, because that's, although I did say that this formula works for all an, including a naught. So a naught is, so one way to think of it is c naught plus c to the negative 0, or which is c naught, or 2 c naught. So c naught is, where was that? That was up here. So that's this thing, just without the 2, because we're multiplying by 2. So this is equal to 1 over pi times e to the pi minus e to the minus pi. And that's a naught. Okay, so that's actually what you get from taking this thing and plugging in 0. And I'm actually not 100% sure if that is always the case. I don't think it usually is. Yeah, because you can, but in some cases like this, it will be. Okay, so Bn, let's compute that. So Bn is I times Cn minus C negative n. So if we, let's see what that is. So if we multiply, if we subtract these things together, now the real parts go away, and we are what are we left with? We are left with this term times 2 times in. Okay, so it's really easy to miss an I or miss a negative sign here. So let's be careful. So this is I times, so the difference here is, now we have negative 1 to the n times n times e to the pi minus e to the negative pi over, we get rid of the 2, pi, that's not supposed to be negative, I just bumped my pencil. So over pi times 1 plus n squared. And now how can we, oh, and I forgot that I have an n here, I really have an I right there. So now these i's multiply to get negative 1. We could stick a negative sign out in front. We could make this n plus 1. We could swap the order of this. Let's make it negative 1 to the n plus 1 times n times e to the pi minus e to the negative pi over pi times 1 plus n squared. And there's our Bn. So these things weren't simple to derive, but I hope you agree that computing Cn, which involved an integral of an exponential function, and then using these formulas, well, once we got into this form, was still much simpler than computing these three integrals, two of them being exponential functions times either a cosine or a sine. And actually, maybe the hardest part here was this business of I don't remember what to call this, turning this fraction into something of a plus bi, which we didn't actually need to do. This was purely to make things more pleasing. We could have done is we could have started right away and just said this is Cn, and then said Cn plus C negative n, and we would have gotten, if we had done that, we would have gotten the same thing if we had done Cn plus C negative n, and we would have gotten the same thing down here had we done I times Cn minus C negative n. That's a good exercise for you to try if you want some practice. Okay, so that's the end of the complex Fourier series topic. We will come back to this later in the course when we study Fourier transforms, which you can think of as a, how do I want to say it? It is like a continuous version of a Fourier series. So a complex Fourier series is how you can, instead of thinking of it as defining a periodic function of period 2 pi, you can think of it as defining a function from negative pi to pi. If you want to define a function of a larger period or a larger interval, then you need to use more and more exponentials. And in the limit, if you want to, you can define a function on the whole real line using, think of a continuous Fourier series. So instead of an infinite sum of complex exponentials, you can write them as an integral of complex exponentials, and that is called the Fourier transform. It is useful all over science and engineering and mathematics, and we will use it when we study PDEs on unbounded domains later in the class. So stay with us.